In this session concerning primary-secondary pumping, we will discuss the length of common piping that can be used with primary-secondary pumping application and proceed from that into equipment room piping practice. Primary-secondary pumping developed, as you will remember, from an initial consideration that we could and would use small pumps to provide the necessary heating on a stop-start basis similar to residential heating with the connection to primary-secondary crossover bridges. Because of the necessity for completely stopping flow when the pump stops, the difference in terms of length for this application means that the T's should be placed fairly close together and the common piping length should be relatively short. On the other hand, for most applications involving primary-secondary pumping, we have, with large pumps, a condition where the pump basically operates continuously. And these pumps can be rather substantial in size, up to the order of 50 to 60 feet of head. Utilizing an application such as this with a control valve in the crossover bridge, we can assess that the length from the supply T to the return T and the length of the common piping can be relatively long relative to the usage of stop-start pumps. And we can assess that if a pump has a head to the order of 50 feet, as an example, that we can utilize about 2% of that head as the head developed across the crossover bridge. Now, this would mean that we could, for this circumstance then, allow about a 1 foot head loss in that common piping. And inasmuch as the common piping is generally sized to the pipe size that we have in the crossover bridge, this means that we can allow a relatively substantial length in the common piping, providing the secondary circuit pump operates continuously as it would in a system of substantial size. So proceeding from that then, these being two-way control valves, we need not apply the common piping for this circumstance and for the general usage of three-way control valves. When the pumps operate continuously, we need not apply these connection points so that the common piping is extremely close. Now, proceeding from this into a discussion of the equipment room piping practice. In most larger systems today, we are utilizing two-way control valves in the distribution system and for control of the terminal units. Two-way control valves are also generally used in the crossover bridge in terms of modifying the flow rate through the primary circuit, primary distribution circuit, so that flow rate then through the chillers could vary unless these chillers are particularly adapted to a basically constant flow. And the classic approach to design of the chiller room, for example, in large system practice has been to employ common piping with each of the chillers separately circulated. This disassociates the pumping of the chiller loop from the pumping of the main distribution loop. And let's illustrate then how this would work on a system using variable volume flow rate. Let's say each of these chillers flows at a rate of 1,000 GPM when its chiller pump is on. And we have for this system then at full load 3,000 GPM flowing through the piping system. As the two-way valves in the system modulate and change flow, the flow change is stated by a flow change in the distribution system. Let's consider the initial full load condition, in which, in summation flow with all of the chillers in operation, we have 3,000 GPM pumping away from the T. We are introducing, however, 3,000 GPM into that T, so inasmuch as water flow into the T must equal water flow from the T, we would have zero flow in the common piping. Now, given that the two-way valves change flow in the distribution system, and let's say reduce the flow rate down to 2,500 GPM, with all chillers in operation, we're still pumping 3,000 gallons a minute away from the T. Because we're only introducing 2,500 GPM, we will then establish a flow rate in the common piping directed to the T at the return side of the chiller loop in such a way that we are mixing 500 gallons per minute of leaving chilled water with 2,500 gallons per minute of return water from the system. This will then decrease the water temperature entering into the chillers, causing the chillers to deload equally and operate so as to still provide the necessary chilled water supply to the system, even though the flow rate has decreased in that system. Let us now assume the flow rate decreases to 2,000 gallons per minute. We now have 2,000 gallons per minute entering into the T, 3,000 gallons per minute being withdrawn from that T, and our common piping flow rate must now increase to 1,000 gallons per minute. Now, given that we have some method of determining flow rate in the common piping, which can be easily determined as through a turbine flow meter, we can, as soon as the flow rate reaches 1,000 gallons per minute, or flow rate associated with one of the chillers, simply take a chiller off the line, and this would return the two remaining chillers then to full load operation. Again, if our flow rate decreases to 1,500 GPM, and we are now, because of operation of only two chillers, drawing 2,000 GPM, we would again return the common piping flow rate to 500, and given a further decrease to 1,000 GPM, we would be able to take the second chiller off the line and operate then with the chillers coming on and off the line in terms of flow determination in the common piping. This is a practice that has been followed for many years and has worked very successfully. Another potential method of using chillers with secondary pumping in the equipment room has been recently developed by Bill Code of McClure's office in St. Louis. And what happened in this circumstance is rather interesting. Bill started out with a basic design correlated as illustrated here, but found through the contractor that there were great difficulties in putting the common piping in the location usually established for the classic position of common piping in distribution systems. So the contractor then proposed that the common piping be placed at the other side of the loop. Bill, of course, went through an analysis of this. And let's see what happens with this type of arrangement. Again, let's say that we have 3,000 GPM as the basic system flow, and we have 1,000 GPM for each of the chillers. Now, this would mean that each chiller is developing 1,000 GPM flow rate draw. So we'd have 2,000 at this point, 1,000 flowing through that segment of the piping, and we would have zero flow in the last, or the common piping section of this illustration. Supposing now, however, that our flow rate in the distribution system decreases to 2,500 GPM. Because of the arrangement of piping, and because each of these pumps and its control and balance is set for a flow rate of 1,000 GPM, we would still drive 1,000 GPM through the first chiller. We would have 2,000 GPM available in the second chiller. We would draw 1,000 GPM through that chiller, but we now have 500 GPM available for flow through the third chiller. Now, if that chiller pumps 1,000 GPM, and indeed it must because of the considerations of piping pressure drop in this illustration, what would happen would be that we would have 500 GPM in bypass, the 500 GPM in bypass of leaving chilled water mixing with 500 GPM of return water from the system. So the chiller would then operate at 1,000 GPM, but at 1/2 load. If the flow rate decreased still further, down to 2,000 GPM, we would still maintain full load operation through the first two chillers, maintain 1,000 GPM through the last chiller, but we have now zero flow, and we have no load, and the chiller would simply cycle off. Again, decreasing the load further to 1,500 GPM, with only two chillers on the line, we would still maintain full load operation of the first chiller. We now have 500 GPM in the piping proceeding to the second chiller. The third chiller is now off the line, and because the second chiller provides 1,000 gallons per minute flow rate, we are now in bypass with 500, and again proceed to intersection backwards now to this point, where 500 GPM of leaving chilled water is mixing with 500 gallons per minute of supply of return water. So this chiller now goes on half load. And the loading of the chiller then goes on and off depending on the flow rate change in the distribution main as compared with the pumped flow in the chillers. This, of course, eliminates the need for the control devices in the common piping, the flow measurement devices in the common piping, which actuate, in the classic example, the start and stop of the chillers. Now, proceeding from this then into a discussion of the usage of primary, secondary pumping with boilers in equipment rooms, we can utilize boilers placed in series, each with their own pump, and operating in such a way that taking their control from the return water temperature, the pumps will cycle, starting and stopping to deliver hot water so as to maintain a basic return water temperature from the system, which can be stated on reset. The basic advantage of breaking the large system down into several smaller units is that the large, oversized single boiler unit establishes a very high seasonal efficiency, a very low seasonal efficiency, because of bypass stack losses in the boilers during low load operation. In this circumstance, because the boilers are relatively small, the stack loss is decreased, and because of the reduction in stack loss, we do establish a very high seasonal operating efficiency. This illustrates the boilers in series with a startup such that if temperature is not maintained, a second boiler is started. If temperature is not maintained through the second boiler, a third boiler, and so on and so forth. We can also apply boilers in equipment rooms so that we apply the supply and return measures directed to boiler application 4 in a manner similar to application 4, the chilled water application. In this circumstance, again, we start and stop boilers in accordance with load. And because we have decreased the size of the boilers, we have decreased the stack loss, and we cycle the boilers on and off as a part of the load need of the system. We have another basic application for primary secondary pumping having to do with the prevention of coil freeze-up for heating cooling systems. Let's illustrate and discuss this for a moment. In a basic heating cooling systems applied commercially, we'll quite often have a coil in the air duct supplying the building, which will take return air and outside air, causing this to flow across the coil to provide either heating or cooling to the building as dependent on the water temperatures being supplied. And the load characteristic for this is quite often stated by a three-way control valve. Now, the problem with a mix of return air with outside air has to do with stratification. And we can stratify cold air so that that cold air bleeds across the lower coils of a heating and or cooling coil. Now, this would mean also that we have a warm air section of return air being delivered across another segment of the coil. Now, should this control valve close off in terms of bypass or flow through the coil, what will happen will be that flow through the coil will cease. And when flow through the coil ceases, the fact of having very cold stratified air going across this coil will cause the coil to freeze, leading to much consternation and great difficulties. But, on the other hand, if we do maintain a constant flow through the coil, the potential for freeze-up is very, very much reduced. So let's take that same system then and illustrate the very simple modifications that are used for coil freeze-up protection on systems of this type. We can apply a coil pump in such a way that the coil pump will provide necessary flow rate through the coil itself. And then if we provide a primary, secondary section of common piping to that coil, even though the valve itself closes to the introduction of hot water into that coil or cold water, the fact of closing the valve to flow from the primary distribution system will not affect flow rate being delivered through the coil itself. Now, what will happen in this circumstance then is this, that we have warm stratified air in one section of the coil, and water being pumped through the coil and in complete bypass now will necessarily increase in temperature to negate the effect of the decrease in temperature caused by the flow of water through the cold section of the coil. So we then have a balance, basically, of heating versus cooling. We should employ for this circumstance a check valve in the common piping. And that check valve, in association with a flow meter, should the pump stop, the valve can be set to an open position through control methods, so that we do establish a flow of water through the coil even with the pump stopped. But the point is this, that the generality is such that the pump in operation at all times will establish a coil freeze protection approach that has been widely used and that does solve a great many of the coil freeze problems that we have encountered in the past. A second method for control of coils such as this has been to utilize a two-way control valve connected across the supply and return main and providing for control of air temperature leaving that coil. Again, we have warm stratified air in one section of the coil, cold stratified air in the other, and should this valve close completely, we can very quickly freeze the section of the coil that has the stratified cold air moving across it. It should be noted that even though we have a fan placed, for example, at the inlet side of this coil, the fact of using the fan will not eliminate the stratification. The stratification will go right through the fan and be delivered simply to another section of the coil in such a way that, again, the potential for freeze-up is very, very high. Again, the solution is to provide a secondary coil pump and to establish methods by which we can be assured that at all times we will have flow through that coil and eliminate the potential for freeze-up. Once more, the secondary coil pump will provide, despite the fact that the valve is closed, the control valve is closed, will provide the continuous flow, and we will heat water being pumped through that coil through the stratified warm air section of the coil, so as to counterbalance the effect of the stratified cold air as this would attempt to cool and to freeze the water itself. There are, I should point out, many, many, many other applications of primary, secondary pumping that follow from the basic design precepts. And these are too numerous to mention. It can be stated today that basically primary, secondary pumping provides a fundamental design tool that will and should be used by design engineers in solving the problems associated with our large, complex heating, cooling systems. And indeed, the directional thrust in terms of industrial application is so wide and so diversified that the application provides for the solution for a great many otherwise very, very difficult problems associated with these areas.